part of his curriculum, or is this extra curriculum?
Yeah, so for Aaron is going to present the physics seminar on Monday, and it's time to start preparing.
Hey, there's no time like the present.
Exactly.
No, there's no time like 10 minutes before the talk.
That's why I stopped talking.
So feel free to write down comments, even very critical. And if Aaron really needs to hit the road, he can just collect our written comments. But if there is some really important question, improving stuff, don't hesitate to ask. I will be back in like 30 seconds.
Okay. So, as Dimitri said, this is for the physics department. So, I tried to put a little bit more of a basic physics ideas aspect to some of these slides. So, what we're trying to do is do computational modeling of photophysics and excited dynamics in general in our group. And specifically, I focus on lead halide perovskite nanocrystals, or quantum dots, as some people might call them. So, this is an image of a quantum dot. You've never seen one before. Very crudely, it's just a chunk of rock. It's like nanometer sized, has surfactant on it. So you can put them into solutions and they stay dissolved. And then these are the observables that we generally try to compute in our group. So we have a photo-excited electron hole. We try to compute cooling rates. So excess energy from an excitation to the band gap edges. Non-radiative and radiative recombination rates. And with those, we can compute quantum yields, or photoluminescent quantum yields, so we can try to model how efficiently these materials emit light. And specifically, we're going to try to utilize I guess a unique physics to these perovskites, a Polaron, and try to get emission out of those for infrared light sources. So this is just a general outline, so introduction, some basic physics ideas to follow along. Methodology, what we use to compute the observables we're looking for, and then results. So it's kind of broken into two, so it's a couple slides on a neutral quantum dot, so no Polaron model, then we're going to start talking about modeling Polarons into the quantum dot. And so I was going to address this slide up a little bit more, so why should we care about nanocrystals in general? So they're kind of versatile, so people want to use them for lots of different sort of nanotechnology. So energy devices, you can use them as light emitters or absorbers, so you can deposit them and make thin films out of them for LEDs or photovoltaics. People are looking to use them as anodes for batteries. So a lot of energy devices, you can use them as sensors. So if a molecule absorbs onto the surface of a nanocrystal, it can light out a pulse, so it can be used to sense molecules. There's also a push to use them for quantum information. So there's a lot of uses for why people are interested in nanocrystals in general. And for lead halide perovskites, the initial reason people are interested in them was from this paper in 2015. So there was a group from Zurich in 2015. They were able to make different kinds of lead halide perovskites, and they can tune the emission from across the entire visible spectrum. So by changing out, I guess they're made up of fully inorganic, so cesium, lead, and iodine, or halides. And by switching out the halides, you can change them from blue to red. And then by changing the size, you can also change their light emission properties as well, kind of a little bit. And this is just a figure showing absorption and emission across the visible spectrum. And then they also have pretty quick lifetimes, and that's generally what you want if you want an efficient light emitter.
Do you permit to interrupt you?
Mm-hmm. No, you can go.
Daniel Ramirez is not with us today, but when he was making seminar presentations, he was showing a piano picture, and then he was not answering question of audience.
There is no
piano. So I'm very confused. Are you going to show a piano picture?
Picture of the quantum
distribution
dot?
of what with I.
There is a two-dimensional color map, with X and Y being like
Oh,
size of nanocrystal and concentration, and then it continuously go of all colors. I'll make a note. So if you don't
Okay, yeah.
Yeah, that, honestly, I don't think it's needed at all.
Okay.
I would not even bother.
Okay. Do not bother.
Oh, the television
Mm-hmm.
standard thing, yeah. Yeah, and that's kind of how they finished this paper. Is they showed that you could use these, and you can get bright colors for
Mhm.
all the, so you can make televisions out of them, or get very bright colors, or brighter than organic, or like organic LEDs anyway. And so this is the big reason why people are interested in these. You can see I took this like a month ago. It's already got an insane amount of citations, so it's pretty popular in the field, and there's a lot of research being done on them. And so a couple of just general physics principles to kind of understand the physics that we look at behind quantum dots. And so to start with, if you consider just like a infinitely periodic semiconductor, like its solutions are the Bloch wave functions. You kind of learn that from, if you take a semiconductor or a solid state physics class, where this U represents like the periodic potential, so that'd be like where each of the atoms are in the lattice. And this phase factor, or this exponential, is like the envelope function for the, so it's basically it's delocalized throughout the whole crystal. So you have a fast varying and a slow varying part to your wave function. If you go from an infinite periodic solid to like a box, like a nanocrystal, you see that our wave functions essentially become like a particle in a box wave functions, where the big thing is this phase factor basically just turns into your sine function. And then if you go through, you have your boundaries for the length of your box, for the edges, and then you have your principal quantum numbers, and you have your energy states here. So if you picture that in terms of like a conduction and valence band, so in your conduction band, if you removed an electron or put a hole, so this would be like the lowest energy state here for the hole. You can see that would have the same type of symmetry you would expect for like an s orbital from your atomic.
Envelope, those are plane waves. Is it correct polar envelope function?
There are two things.
It's the slowly varying
Due
part.
to the confinement, due to the boundaries.
No, he's saying that
For
each
the
I
wave
can
function, e to the
R.
I, K, R, those are plane waves.
In a broad sense. It's infinitely delocalized, so it's, I guess I wouldn't call it.
Plane wave that contributes to the wave function converts into envelope function if the system is confined and lacks pure periodicity, because of Euler function. This slide misses e to the power minus I k r. It's can you index?
No, it's sine, the same, you can write it as minus IQ.
Next line, before the equal sign. Yeah, here it should be like e to the power I k r minus e to the power minus I k r, and then it should be exact. Because in the confined system there are like two incident waves in the opposite.
Oh, and they cancel, are they?
Oh, they
Or their phases match, or-
created this envelope functions.
They
create
Both
standing
nodes
waves.
and to the
Constructive and
maximums.
destructive interference and form these nodes, right?
Oh yeah, so maybe better, it becomes a standing wave. So it becomes your sine.
Exactly.
And the property of the standing wave will be completely dictated by by the size of the box, right?
Mhm.
Whether it's
Yep.
cubic or square, or how to call square or sphere or whatever.
Mm-hmm.
So
So yeah, but, and then I'll bring this up later in the slides too, so it might make more sense when I get there. But basically the point I'm getting at is you can expect, when you look at your orbitals for your quantum dots, you'd expect them to have, this shows similar types of symmetry for like your S, P, D atomic orbitals, yeah.
It's a little confusing and unclear. Is it ab initio simulations or it is pure modeling?
This is just pure modeling, so this is,
Label it considered to label it.
Okay. So yeah, so the band gap is just a parameter. We put it, we just use parameters for L, M, and I guess those are the only two parameters, and N. And then we chose the effective masses that are.
And this again, you have spherical well here, right? This is a solution for spherical or for what?
Particle in a box. So
Which box? What
a
size of?
three-dimensional box.
Cubic box?
Cubic, so like 10 nanometer.
So you can figure index on these cubes that you are showing and tell those are the boxes, and the golden.
But if it's a cube, why you go into the dependence on R in your left side?
Did I?
Well, because I thought that
Oh.
R here means you are in a spherical coordinates, no?
It could imply that. I guess.
So here you just in X, Y, Z, and R is just the regular, small r doesn't mean that it's a R which we use for spherical coordinates.
Right, I guess it's composed of X, Y, and Z coordinates, and they're all orthogonal. So I could make that more clear too. And that's just for this modeling that we did here. We made up all the directions orthogonal. So it would be going, so if this was like the edges of our box, normal would be X, Y, Z.
I guess you just need the word that this is a solution of, like your wave functions, right? Solution of particle in a cubic
So
box.
it's three-dimensional?
Or three-dimensional particles, cubic box, right? X, Y, Z is the same?
Yes,
It's a
I guess
cubic
they're a little offset, so we could show broadening for our P. If they're exactly the same, this
Then
would
it's rectangular box.
true. Mostly square. Strong approximation, it's square. But yeah. So for our holes, and then photoexcited electrons too. If you have a photoexcited electron, you expect them to behave in a similar fashion as a particle in the box for nanocrystals. And so that's just for kind of understanding, having a general idea for electronic structure of nanocrystals. And so another unique things about perovskites is that they are polar crystals. So that means that there's ionic bonding in these. And so if you have photoexcited charges like an electron or a hole, in this cases, they will interact with the ions because they have charges on them. And then the ions will move in response to the charges. And so there's a electron-phonon interactions, or a coupling between the charges and the lattice. And essentially what that does is, in this case, it's weak, so the ions do not move very much from their equilibrium spots. But in the case where you have Polaron formation, you can see that this photoexcited electron, you have positive charges moving towards it, and then the negatives moving away from it, and vice versa for the whole. So it essentially confines, or kind of traps your charge. And then there's different degree of Polaron formation. You can have strong Polaron formation or light Polaron formation. And in perovskites, they see that the charges are mobile, so it's like an intermediate coupling. So it's an intermediate Polaron size. And another thing to point out here is, so this is the potential well, like the localization of the charge, and there are bound states. And you get bound states within the Polaron electronic structure. And so we good with that? And then, so the way that people describe these rigorously in the 50s, I think, there was a man named Frolich. He came up with the Frolich Hamiltonian using crazy second quantization notation. But basically you have your electronic energy, your phonon energy, and then your cross-coupling electron-phonon interactions. And so this just represents, is this showing up?
It doesn't really work that
Yeah, it's pretty dim. So this just gives you the creation and annihilation operator. So it just gives you the electronic energies of your orbitals, your energies of your phonon modes, and then this is essentially like a scattering of your electron and your phonon.
What's that?
What's what?
On HE, the first Greek, no HE, up 2 lines.
the electronic Hamiltonian energy, right?
What is that Greek letter stand for?
It's just the energy. So an energy is a function of n, so that's a number, so your electron, k is momentum, and then s is spin.
1 is to E.
That's how they cited it in the paper.
Okay.
And so, yeah, so this is just your essentially electronic energy with your indices, and then this coefficient here is your essentially your coupling energy. The energy is a coupling between the two
And
states.
again, what is your S, the set index here?
That should be spin.
Oh, spin, okay. So you have electron label of electronic states, all states.
Number of electron.
And with spin,
Yep.
including spin state.
And so generally the solutions to these, they involve crazy Feynman path integrals because it makes the notation simpler, but there's easier ways to think about or more.
What is alpha?
Oh, so this is like a coupling parameter that describes the strength.
And how does it differ from gamma?
It's not in your Hamiltonian, right? Then how
No,
do
it's
you-
parameter of gamma. Like gamma n and prime depends on alpha.
Ah.
But like why it is so subordinate sequence? Why don't people call gamma electron from coupling?
That's a good point, I don't know. But I know usually when people talk about like the strength of the electron interaction, they call it alpha.
Okay, just consider adding it if possible.
Or maybe because your gamma depends on the other parameters as well, on the phonon
Mhm.
frequency, right?
Usually the phonon, the free phonon term in the Hamiltonian in second conversation language is h bar omega a dagger a plus 1/2. The whole thing in parentheses.
Right, it's just depends how you define your coordinate because of the zero. So it just doesn't account for the 0 point energy, I guess. Yeah, it's just a scaling factor. So like the energy differences between all your states should be the same.
What is Q and B or D in this one for phonon and
Position,
Phonon mode and
yeah, it's like ionic and vibrational mode. Position and vibration.
Q?
Isn't that usually position?
But then in your electron phonon, you have a subtraction of k minus q. So it prompts that maybe q is momentum of phonon mode.
And you?
U is index of phonon mode, of normal mode.
And you?
And q momentum of phonon.
so if you create a phonon with momentum k, you've got to annihilate a phonon with momentum k minus q because of momentum conservation. But usually the free phonon Hamiltonian, I've always seen it h bar omega in times parentheses a dagger a plus 1/2.
Oh, you mean third line?
Yes.
But again,
It's just
transition.
changing total energy. You will not affect
It's
anything.
change total energy, and again, we apply it in the sense that you have, you switch between the one phonon mode to another. That's why it's not really the energy by itself is important, but it's splitting between the energies.
Okay, so
Right.
the physicist
So
may
that's-
ask that because
Yeah, but
They
again,
see
it's not,
harmonic
this
oscillation.
shift, how they already answered, right? This shift is not important physically because what is really implies into this phonon interaction is change between the energy of phonon modes, right? And then it's HU.
And so yeah, second quantization, it's like, I haven't taken field theory, so I'm not used to all the notations, but a simpler idea, or way to think about these is consider a simple model. So back in the 50s or 60s, I guess 56, Walter Kohn. He was considering how to make these many-body problems simpler to deal with in semiconductors. And so he found that if you add an electron or a hole into an insulator or semiconductor with a weak enough Coulomb field, that you can rewrite the many-body problem just into an effective mass problem with a Coulomb interaction. So it's basically your
Central field.
yeah, just like your atomic atom problem from PChem or whatever quantum physics class that you took. And so it's basically just your kinetic energy and then your 1/r potential, and then whatever your wave function. So a simple way to think about what your electronic structure for your Polaron would look like is essentially your Polaron wave function would just be some sort of scaled version of your hydrogen wave function. You probably wouldn't have the same principal numbers, but it would depend on some sort of quantum numbers. And so you could think of the energy, or like the depth of this well as being some scaled factor of whatever the binding energy is compared to the neutral state or the conduction band state, just scaled relative to the Rydberg energy, that's what they call it, or the bottom energy of your hydrogen wave function.
And blue lines correspond to this
The one over-
attractive Coulombic potential.
Yeah, so this is the 1/r potential. So the deeper you go, the stronger the Coulomb interaction. And you expect these bands to be to show the same, like some sort of symmetry
I
as
have
your
a
hydrogen
question. So
problem.
the unoccupied states don't get affected by this. It's only the occupied states?
Those are all conduction things.
No, it says LUMO.
Yeah, so this is just showing like if you put in if you add an electron, like you'd have it would occupy the LUMO initially
Okay.
at like the first
You can
instance.
do the same for holes, right? You can do the
Yeah, same for holes in the valence band. And then you have nuclear reorganization, and then it forms this bound well.
So then that's no longer LUMO when you do this.
Right, this state wouldn't
It's
be.
like creating gap states, the mid-gap states, right? So you have
So
this bound state
I'm not saying
appearing in the band gap.
Levi is looking for strict definitions, not
Yeah.
for
Right.
essence.
Because when you say
So it is
LUMO,
LUMO of intrinsic material before defect was created.
No, it's a pure electronic state. Luma stays for the electronic state. But if you have phonon kind of contribution coupling, you have this mixed states due to the Polaron formation.
yes, but then. the
That's why
Polaron-
these states technically they're not pure electronic anymore. Yes, this is
but
why they not
typically
call
when you
Luma
say
as the very
LUMO,
last one.
That is the states, that is the lowest in energy that's
Right.
unoccupied.
This is
Well,
exactly
just-
why I'm answering your question. If you
Yes.
want to be so,
Rigorous.
picky about the definition, Luma belongs only to the pure electronic state. If you have coupling to phonons, you cannot call it electronic state anymore, right? It's vibronic state. And then Luma definition is not applicable anymore. That's why they don't use it.
Then why is it on the top?
Because this is Luma for pure electronic state. If you don't
It's a
have Polaron interaction.
It's a reference.
It's a reference
Um,
before you
if-
add the Polaron.
If one wants to be like very rigorous, one may do two images. One with this gray bar with LUMO definition, and next one the same image as we see, but without this word for LUMO. So it refers to reference structure, right?
Mm-hmm. And in the literature, they normally how they name it is, they've named this the Polaron ground state, whatever your bottom rung is. And then your second rung, they call it the relaxed excited state. And so that's why I'm going to refer to those throughout the rest of this
What's the
presentation.
excited state?
The
Oh,
relaxed,
Huh?
the relaxed excited state.
Which of them?
So it'd be the second lowest energy.
But again, it's for electron only, right? You kind of look on them as a separate, it's not, like it's in the picture that you have electrons and holes not coupled together, right?
Right. So if this is like your electron polaron, like it could be possible that it could absorb, or it can make transitions between these things. And so, I may not get your question again, but usually whenever I look in the literature, they call this just the Polaron ground state. And then this is like the relaxed excited state, because this is like the most stable excited state before it recombines to its Polaron ground state.
And there is one thing that may induce like curiosity or hidden questions. Most of us are playing with excitations promoting electron from valence band to conduction band. And both electron and hole are single particle, right? One neglects the rest of electrons. So here, Aaron focuses only on electron, which is like one particle in the band. But one can apply absolutely the same approach to reading the hole, which is also single particle, which may follow hydrogenic potentials and hydrogenic orbitals.
Yeah, so this is only half the picture. You could have the same thing, just just flip it upside down or invert it. And I'll be mostly focusing on the hole too, so we'll see images for that. So this is how you can think about the electronic structure of polarons. And it's a little light on details, but one paper I found is if you have a polaron with their appropriate alpha value that we kind of talked about earlier that describes the coupling or the strength of the electron-phonon interaction, they find that you can treat optical transitions between the polaronic states in the same way as you would for like light-matter interactions. So if you could get an energy source that was in resonance with these rungs, you could have optical transitions within the polaron well, which come from basically, which follow Fermi's golden rule. So you can use transition dipoles.
And E stands for electromagnetic.
Yes. And so what we try to do is, we got a little greedy, so we want to go a couple steps further beyond just modeling optical transitions. We actually want to model the kinetics of optical transitions and also non-optical or non-radiative transitions between the polaron electronic states. So this is what we attempt to model with our atomistic Perovskite model, is a photoexcitation from the valence band to the conduction band. Model the cooling of each respective carrier to the polaronic ground state, or the polaronic relaxed excited states for electron and hole, and then get radiative and non-radiative recombination rates between those.
So kind of related to the questions and discussion which we had before. So your picture is really considering again an independent free electron hole pair. So you, as humans, you excite free electron hole pair as a very valid picture in the conduction materials, right? Because your electron and holes really not. But as soon as you bring confinement, right, your electron and hole cannot be far away anymore. And you really force them to be interacting with column interaction. And you kind of enforce the column interaction and excitonic effects due to the confinement. So also, but again, you neglect by this effect despite your confinement. Also, the question is, if you neglect the excitonic effects, you always can say maybe they're small, but you need to justify that they're small. My understanding is that your Polaronic effect usually is a second order effect comparing to the excitonic effects. So if you neglect excitonic effects, then it's kind of strange that Polaron are stronger than excitons. So my question is, it looks like you probably need to justify your model. First, at least you need to prove that despite confinement, you can neglect the excitonic effects. And second, maybe compare the strengths or rates or time, I don't know, whatever parameters can be used to compare excitonic effects in these materials to the Polaronic effects. And say Polaronics is definitely more important, more stronger.
So I think
Polaronic couplings killing, overwhelming the excitonic effects. That's why we're not considering excitons. We consider free electron hole pair despite the confinement, but we're focusing on the Polarons.
Right.
You see
So
my logic, right?
I think so. So you're saying that we create the photoexcited pair. You're saying that usually the exciton effect's first order, so the electron and hole are going to bound together first before separating.
You create the bound state by itself, right? And then the electronic structure of exciton, of course, would be different than free electron hole pair if the excitonic couplings are strong.
Mm-hmm.
And again, strong, you compare coupling electron hole interaction through the column or whatever, right? Should be much smaller comparing to your band gap. Then you say, yeah, it's perturbation. But at some orders of magnitude, we can neglect it. But then, of course, Polarons also perturbative term. And then it has to be at least larger than excitons.
I get what you're
neglect
saying.
excitons.
And I think one thing is, well, I guess I don't know how that theory is laid out in general, but I guess in polar crystals, especially in
polar crystals.
in a polar crystal, so there's a very large dielectric screening in the lattice, so
Which were
like
typical values?
it's like in the thousands,
Yes.
so so typically there is not very much attraction between these, and to get any sort of Coulombic effects, you really have to squeeze them below the Bohr radii for perovskite nanocrystals anyway.
So all
What is a Bohr radii?
It's like 7, 8 nanometers
Okay.
for this particular.
Okay, so it looks like you definitely know all this data. I'm just thinking that you probably need somewhere, before you go to the details for your model, right, you kind of explain how it is possible to treat. You probably need one extra slide just saying, this treatment is valid
or
because,
maybe just in this slide,
or
tell
in
us
this slide
like
somewhere.
dielectric constant epsilon is around 1000,
Big.
and then all excitonic effects are 1000 times smaller than it would be in otherwise.
But on the other hand, because it's very polar material, then your Polarons will be kind of enhanced to this strong polarization, right?
So in this specific material, Polaronic effects are bigger than excitonic
Yeah.
effects.
And if you say it somewhere here, then I guess it would be clear why then you go with the language of just free electron hole pair. No one will be confused with it.
I get what you're saying. So yeah, there's definitely space down here, so I can fit that in.
I have a question.
Yeah.
What is, in the previous slide, what is VEM in the Faraday golden?
So that's just the coupling potential of the electromagnetic field.
What's the electromagnetic?
Yeah, that's what I meant by EM. So it's just dipole operator, essentially, or transition dipole.
Okay.
And so, go over some of the methodology that we use to do these things. So we're computationalists. We don't solve all these equations by hands because it's a 1,000 atom system, 2,000 electrons. So we use density functional theory, and we use vast software to compute the orbitals. And so the orbitals that we have to use for perovskites in general they're called non-collinear spin Kohn-Sham orbitals. And I guess the reason for that is on the bottom, but the reason we have to use non-collinear is because there's strong spin-orbit coupling due to the lead atoms in the system. And so it mixes the spin and angular momentum states, so it requires to use non-collinear. I haven't thought of a good explanation of why we have to use these specifically non-collinear
Energy
orbitals.
should have only one spin index. Probably sigma prime, same as all. Epsilon sub I, comma, sigma prime. Operators have two spin indices, and energies have only one spin index. Just remove sigma
Okay.
if time allows. Sorry for interrupting, please keep going.
And so the solutions to the non-collinear equations are spin orbitals or spinor Kohn-Sham orbitals. So they're just two component spinners. So it's analogous to like Dirac, or solutions to the Dirac equation where you have 4 component spinners, but since you can neglect 2 of the components because they're very small compared to the other 2 components, and so in VASP they implement 2 component Kohn-Sham orbital spinners. And then I was going to put some stuff about just orthogonality and orthonamity. I think those are the 2 terms I wanted. Here, just to show the properties that you would expect from the spinor orbitals. And we include relativistic, or VASP in the software includes relativistic corrections for the energies of the eigenstates. And so, as shown here, and this is basically just the dot product of the angular momentum and the spin, which mixes the spin components. And from our Kohn-Sham orbitals, we use those to compute observables for the system, so density of states. So basically, we just sift through all the density, all the energies, and then we provide a broadening parameter to give them some thermal width. And we compute absorption spectra of our Spinor Kohn-Sham orbitals using transition dipole operators. So this is just two orbitals with the position operator, so transition dipole operator and the Spinor notation. And then with the transition dipole operators, we can compute oscillator strength based on the dipole and the transition energy. And from the oscillator strengths, we can make an approximation of the spectra and the independent, I probably should have said that to begin with. We use the independent orbital approximation for our absorption spectra, so no Coulomb interactions. And so basically just sift through the strength of the oscillator strength for each energy and then build a spectra that way. And so that's how we treat our ground state models. And for our Polaron models, essentially what we do is we take our optimized neutral model, and we treat that as our electron and our phonon interaction, our Hamiltonians. So that gives us our neutral model of the energy. And then we approximate the electron-phonon coupling by either adding or removing charge, so N, to the Hamiltonian, and then letting the model optimize around that new charge. So that's what the delta R is. So basically we just put in a charge and let the model optimize around the new charge. That's how we approximate the Polaron, or the electron-phonon interactions.
When you say let the model optimize, what do you mean?
So like how you would,
So run an LCF calculation?
yes.
So obtain new eigenvalues.
And new atomic positions, because the nuclei,
Okay.
so that's what this delta R represents. It's the movement of the nuclei in response to the additional charge.
So your question was like recompute electronic structure or optimize geometry?
Yes.
So optimize geometry, see in the varying geometry optimize last line.
And then all the results I have is for the, I'm going to show for this presentation, for dynamics anyways, for the positive Polaron. So that's essentially just removing a charge and then letting the model optimize. And so those are how we model the ground state observables for the system, or the static observables. And so to model the excited state dynamics, we used mixed class quantum classical methodology. So we treat the atomic nuclei as point charges, and we treat the electrons quantum mechanically. And so I guess it's awkward to go in there. And so I guess the machinery that we use is the quantum Liouville von Neumann equation. So basically it describes the time evolution of electronic density using the ground state energy of the model plus some coupling to a phonon bath, which represents the dissipative transitions. And for the model that we're looking at here, the dissipative transitions come from electron-phonon interactions, or essentially thermalization. And so we use molecular dynamics, or adiabatic molecular dynamics, to model electron nuclei interactions. And from those we compute non-adiabatic couplings on the fly. So what we do is, so we have one Spinor Kohn-Sham orbital, and we compare it to a Spinor Kohn-Sham orbital updated one ionic step for the molecular trajectory. So that's what this delta T represents. And so if you imagine if we didn't update the the ionic steps at all, this would essentially be, they're both I indices. I guess this should be a J, shouldn't it?
It should be, yes.
Should be J.
Yes, one I, second
Yeah,
J.
so it should be two different orbitals, so I and J. And,
You were the first to find this typo.
yeah, because the way I was gonna describe it is if you didn't update the positions at all, they should be orthogonal. So this product should be 0, but since we update the ionic steps a little bit, it breaks the orthogonality and you have orbital overlap. And that gives way to dissipative transitions along the molecular dynamics trajectory. And so we compute non-adiabatic couplings along about 1,000 picosecond molecular dynamics trajectory. And then we post-process them into transition rates. And so essentially that just involves taking autocorrelation functions of the non-adiabatic couplings along. And then taking Fourier transforms of those, which essentially gives you a spectral density. So it gives you the phonon frequencies that match with electronic transitions. And in using Redfield theory, you can take these transition rates and sum them together to essentially get your dissipative transitions. Mm-hmm.
It would be a little confusing, too many information for general unprepared audience, and one may decide to help audience to navigate through the slide. So there are two ways how to digest it. One from the top to the bottom, and another is from bottom to the top. So maybe selected by same symbols, like there is a dissipative part, which is provided here, which depends on Redfield tensor, which is provided here, that depends on this gamma coefficients.
Mm-hmm.
And maybe select them by little color background, same color, like red in red, whatever. Or one can read.
I might just move this down here, maybe.
Maybe, yeah, rearrange it to help to digest. Or one can read it from bottom to the top. So first, one starts from non-adiabatic couplings that you excellently explained how they related to orthogonality. And then they are fed into expression of autocorrelation that gives rates, that feeds into Redfield tensor, that feeds into dissipative term, that feeds into equation of motion for density.
Mm-hmm.
There could be questions during formal presentation.
I would expect questions about this. I would particularly after I gave my midterm capstone presentation, because I straight up told them that I don't rigorously understand this part, so they're probably going to be asking you about it.
I have a question first.
Mm-hmm.
Well, what is FIK in the Liouville? What is that?
Oh, it's just the Hamiltonian.
FIK.
They call it,
Why Hamiltonian? We just
it's the many-body Hamiltonian. So like in quantum chemistry.
Tell Fock operator.
Fuck up right now.
Oh, it's fine to have somewhere. Andre's going to be mad if you don't do that. He was mad at me for that.
So it's just your many-body Hamiltonian, electronic Hamiltonian.
So one electronic operator.
Fock space.
Wait, it's a single particle picture.
Yeah.
It's analogous to Hamiltonian, but it includes self-consistent consequences of interaction with other electrons.
That's where they go for operator.
Yes. Yes.
Okay. What does it stand for? What?
Structure and meaning of Fock operator is the same as one electron Hamiltonian. But it is different from Hamiltonian because it includes many electronic effects. Okay. Therefore, instead of letter H, one uses letter F.
Okay. What interactions are included in this Fock operator?
Just maybe it would be reasonable to give reference to like very basic textbook on Hartree-Fock theory. It includes only exchange.
Only exchange.
Only exchange. So it misses Well, it includes Coulomb and exchange and pieces correlation. I don't know if everyone will be seeking for this.
So it's the Hartley folk.
Okay, and
And is that inside that integral? Isn't that just the direct product, right, between phi I alpha and phi j beta?
this?
Yeah, but isn't that just a direct product?
It's not direct because it's changes in nuclear position.
You can't write that in terms of bracket notation.
Oh, you could.
Why presenter, Aaron, uses this explicit notation?
Yes. Why?
It shows the
Because-
spinor component.
Because it is, yes, he's right, because it is Spinor, which is not intuitive for, it is not always used, and one needs to highlight that both alpha and beta spin components contribute to this non-radiative transitions. So it is a scalar product of this rho vector, two-component vector, by Coulomb two-component vector.
Okay.
Make sense?
Yes.
So it will be like summation of two direct products,
So it's two direct. Okay.
like phi I alpha and phi
Yes.
j alpha plus phi I beta and phi j beta.
I see. I see.
So the last takeaway point from this slide is one of the observables that we're concerned with is the non-radiative recombination rates, and we can approximate those just by pulling the matrix elements from the Redfield tensor that corresponds to the transition that we're looking at. So if it was like non-radiative across the band gap, you just look at the HOMO-LUMO matrix element. And I didn't put any other pictures in here. So this is just basically a visualization of the Redfield tensor or dynamics. So basically it's just a bunch of a matrix of off-diagonal elements where that just connects two different orbitals based on the non-adiabatic couplings. And where the height represents the the intensity or the rate essentially of that transition. And you kind of see states that are very close to each other are generally high in intensity. The very high ones are due to degeneracy of states because each band is twofold degenerate. So across the molecular dynamics, their energy difference is only like 1 milli eV. So that's why these are really high. But then as you get further away from a specific state, the transition rates decrease pretty quickly, which you'd expect from like a Boltzmann statistics. You'd only expect intense transitions within a small energy difference away. And so, first part of the results, just some basic results from the charge neutral model that I described earlier. And so, this is just a plot of the density of states, so 0 is the Fermi level, or it's plotted with reference to the Fermi level of the model, and there's a band gap of 2.38 eV, which is approximately what you'd expect or it's about the correct band gap for actual realistic models, but that's just due to coincidence, just the cancellation of errors, so it's just happenstance that we have the right band gap. And another feature that we see from this figure is you can see distinct peaks near the band edges, and so if you remember the particle in a box states from earlier, you can kind of analogously call this your lowest energy would be like your S symmetry for your hole. And then this peak could be corresponding to your P symmetry for your hole and so on. And just to show one explicit example, and so this is the HOMO orbital, or so this would be like the hole state for this model. And you can see, if you just look at the model, you can kind of see that from the edge. Like the envelope function definitely looks like a sine wave, like how we were talking about earlier. And if you project it onto a 2D, or if you integrate over two of the axes and then plot the charge density, you can see that these lines represent the periodic potential. So the slowly varying, or the high frequency components. And then the envelope function would be like a sine squared. So just kind of a cool illustration of showing the symmetry of the orbitals for this model.
Go to previous slide.
Previous.
Oh, previous. The one with the grid.
This one? So X and Y are just orbital indices. And then Z is the transition rate in inverse picoseconds.
I mean, I have a problem when you present. I understand that you have 40 minutes. It's a long, kind of long discussion, right? A long presentation. But even for long presentations, you should be very clear what is your important points. What is, like, you need to help your listeners to say, oh, here is, like, my main thing is to answer this question, right? And it's, I may be missed because I came a little bit late, but I missed only 5 minutes. I doubt that you really put this. So first of all, we need to clearly say what exactly you want to do, like what physical or chemical question you want to answer, right? And of course, then in your introduction, you should probably explain why it's important. And then the tools which you use to do it. And again, for tools, you probably can say, well, this was already developed. We just repeat the procedure which kind of well known. And these things which we modify, and this is our kind of our contribution to these things. Because right now it looks like you put in technical things, you put in analysis of some things. Everything is just kind of spread equally all over this 40 minutes presentation. Like showing this, from my point of view, this is just technical thing, right? This is a tool which you use. This is not something which is really needed for me, who is not going to really apply this methodology. Let's say if I'm experimentalist, for me all the things probably not so important. Or you can use this to explain some things which is important as your main observable, right? But I'm lost now with all your technical things.
So it's not a problem.
It's not a problem. I'm just saying it's boring.
It can be fixed. It can be fixed really easy with like 5 minutes of updating. So your second slide, you do not need to go there. You will have printout. Has the schedule of your subjects, and you may consider to copy paste this navigation slide after each second or each 5th slide and frame where we are right now. That's one thing. Another thing, at the very beginning.
Just say it.
Well,
just tell me, okay, this is just technical thing. It gives me this and this information which we will use for or answering our main question.
But
this would be good enough.
To say it, you need to be very energetic. You need to drink a lot of coffee. But if slides are there, you can just relax, show like, okay, we are here. And another thing, how to fix this perception of audience, maybe at the very beginning, do not keep into like in mathematical theorems. Summarize your main findings. Tell like, I found really interesting thing. And tell like, Polarons do not emit, although I expected it. And I'm spending 40 minutes of your time to prove it.
Yeah. So can you really tell me what exactly your main goal with all this methodology which you derived? And was it really derived by you or not? Okay, let's start with my first question. First, all these formulas which you were showing, right? Is it something what you really derived? This is the part which you were doing by kind of as a new methodology, or you just adapt this methodology and add something new just a little bit?
I guess. The
Actually, I do
spinners.
know the answer to my question, but I think, again, you probably can tell it to people who maybe really will be confused.
Mm-hmm.
So all this methodology is pretty standard, right? Or no?
And
Yes.
even good references, maybe at the
Then
bottom.
you need some references so people know, oh, if I really need the details, I can just go to this paper, read it carefully, or this or this or this paper, read it carefully, and then I will understand what's going on. Anything which you developed by kind of on your side, or something which is not very trivial or very known at this field so far?
Well, I guess what do you mean by
From a
develop?
methodology point of view.
Getting calculations to work, just technical code.
What about this spinners, or whatever, this approach? Is it very
You
common?
can like testing, debugging, verifying, Spinor versus spin polarized. It's also part of theory, and you can claim your credit.
We have another question there, right?
I have a question. What level are you presenting this to? No, I mean that's.
It's a perfect question.
Are
yes.
you presenting it to undergraduate people? Are you presenting it to graduates, prospective students, or people?
Physics department symposium.
Diane probably
So-
can help to answer. Who is coming to the physics
Yeah,
seminars?
who's coming to this thing?
Grad students and professors.
Probably 4 or 5 physicists who are into soft condensed matter and classical, mostly classical physics. There will be.
Are they
Andre
undergrad
is the only
students?
one who does.
Undergrad students usually come to physics?
Undergraduate students don't come
Don't.
to this. The graduate students that will be there are all either experimental physics or educational research.
Okay. So then, I guess my biggest question is that I know the value of having this slide or this equation in there. It explains, where you're getting the graph from or where you're getting all this data from, but I guess, is it necessary to have it in there?
Absolutely.
Yeah?
If he misses it, he will be hammered and chewed.
Okay.
But
It's even for the specific
again, it
audience,
has
it
to
could be
be-
not enough. They will be.
probably the words which you tell it probably has to be really help people to navigate through it rather than really dig in them or insert them to the technical details on that slide, right? Because again, it looks like there will be probably really a few people who really interested in all these technical issues, right? But they want to know the general idea, but they're probably not so much interested in all these small picky things.
I thought that Brandon said that when he gave his seminar.
It's a different story because in his case it was like exam.
Oh.
It was for his BS degree, right? That's why people were definitely much more aggressive in a way to see whether he understands the things which he's talking or not.
But Dr. Krzyzewski will
Ask questions.
stop you in the middle, ask aggressive question, and put in doubt your.
I mean, you
personal
definitely can
information.
have questions. I'm saying that you need this slide, but you probably don't need to spend so much time with going and going and going and going in all these technical details. But you need to give just main ideas, and if there are questions, you go into the details. And again, you probably need to think very, very carefully about what was really the most innovative part in this approach, in this methodology. The most recently involved, maybe it was not exactly done by you, right? But at least by your group, something which was not used, let's say, 5 years ago, the same methodology was not having this thing, or no publications having these things, right? And probably again explain why is it important here, why you cannot, why really you need these spinors, why you need these spin orbit couplings, why you need these relativistic effects. Because of course initially this methodology was done probably without these things, just neglecting the spin state, thinking that everything is in its singlet states, right? And spin and even number of electrons. Then spin is not really a needed property here. So put put really a little bit more physical meaning into your equations rather than go to the kind of step-by-step explaining the technical steps. Because I'm 100% sure you know the technical steps. And if there's a question asking how you get this or how you got that, you definitely probably will be able to answer it. And again, we can ask all these questions later on if you want us to really ask you sharp questions on the methodology. We can really just make you the exam on your methodology. But for 40 minutes presentation, really going, I mean, I was lost, not in the sense that I lost in this specific equations, because I have seen it many times in old Dimitri's presentations, starting when he was a graduate student. But I was kind of losing the main point. So what exactly are you going to do with it? And what exactly your contribution in this methodology? Because if it's just software, which is everyone can just download, click on the buttons and you are done, right? Then why to spend so much time on this? If it's something new in terms of really deriving the methodology, then you need to explain exactly these new points, or at least these things, right? Am I right that this Spinor approach is kind of new in this specific context of this dynamics? Not, of course, for the electronic structure calculation, but for the dynamical, for the implementation into the non-abiotic dynamics. Yes or not?
There are very few papers.
Okay, good.
And like there is
Not from you.
only from the group.
Okay, so then it's
So
really
there are
contribution of
papers
the
by
group.
Dr. Khan, and there are like papers from Aaron, no one else in the world. So
Then don't be shy.
It's very unique.
Tell it, and this is exactly the point where you can brag a little bit about it. Right? And people will again pay more attention when you say the overall methodology is well developed already, right? You can say initially it was blah blah blah, and you can show, of course, the citations where people can read more about this methodology if they're interested. Our contribution, or my contribution, or the most recent part which was added to this method, which is absolutely needed for my systems because, and you then give a reason why these spinors, why you really need them, right? I mean, again, kind of you tell it somewhere in the beginning. We kind of understand that we have cesium elements and so on, and they have open shell.
High angular momentum.
Yeah. Kind of people understand why you need these relativistic effects, but probably you don't be shy, really attract attention to this thing.
So I had a question on your introduction. So if you go to slide 5, we were talking about involved crystal to nano crystal. You spent a long time explaining going from block wave function to particle in a box. Do you think this is really necessary?
No, I will put it in a different context. How this is connected to the methodology which you're showing just like a few minutes ago? Are they connected? Ooh, this is where they're connected. But they're connected in the results. But the methodology by itself is not.
Right.
So it's actually this thing is needed to interpret your results.
Yes, it is a reference point that helps to interpret the results.
So my thought is, do you need to go through about 4 minutes of explaining the math, or could you overview it very briefly and say, through this approximation or this method, we can look at the overall wave function of the nanoparticle, and we see that we get superatomic wave functions, SP, and so forth. And then if anyone asks you about the method and the question, you can make a supplemental slide where you pretty much copy this slide to it, and then you don't have to.
What you're telling would be great. Like if this talk would be practiced like 2 or 3 times more, it would come up
But
naturally.
his talk is on Monday already, right?
But
You give it on
it
Monday.
is just the first dry run.
But he's really short in time because he has only a weekend to
Yes.
change it. But this is a great idea, but I will a little bit rephrase it in a sense. You can have really very extended slide with all this information. there is no need to go through all the details which you have on the slide. You can really spend a little time having all these many things happen in the slide. You can kind of navigate people only through the most important things. But if they have questions and you return to the slide, you don't need extra. You can return to the same slide and now go into the details because all these details are there, right? Or people who are familiar with this material, they will read it from your slide, although you not really talk about it by yourself. So I would say you probably don't need to change the slide, again, because of the time. But when you present the slide, you can probably, again, reduce time on going all these technical issues. Instead, tell, this is the simplest model, which is very easy to use, right? Everyone, doesn't matter whether experimental, like undergrad students can actually create this, who take in quantum mechanics courses, create this very simple model, right? And get some approximation about the electronic structure of these quantum dots, their orbitals, the shape of their orbitals. However, this is probably not enough, right? Why actually we cannot just stop on this simple model? Why you need to go to this very complicated methodology with how many equations you have in there, right? And again, this would be again your transition. This very simple, very transparent, very easy to understand, especially can be easily applied to experimental data and see, for example, this confinement effect or whatever effects you want to explain, right? But this is not enough to explain these Polaron properties, and of course
because there are no point charges, they are not moving.
Right.
It's just a box.
It's an oversimplified picture.
And there are no ligands, which are critically needed.
And then you go exactly again, you kind of highlight again the importance of Polarons and so on, like kind of you go pretty much to your motivation, connecting your slide, whatever, number 2 or 3 with this methodology part, connecting it to the things which you are telling a little bit late, right? Then you go to your very complicated methodology and again highlighting new things and the most important parts which were developed, introduced into this methodology based on the physics which you want to describe, right? Not just going one by one equation, but if there is a question, you can really go into the details and explain in each equation for 15, 20 minutes how much you want to take. But in your presentation, again, think about what is really the most important in your physically meaning of these equations. What exactly the questions you're addressing with them? And what is the most kind of new contribution into this field from your side? And why is it important for the specific systems? And then again, you just again navigate people through your equations. You don't explain, you're not lecturing, right? You're not really expecting that the audience will be able to take a quiz and write all this equation by themselves after you're done with your lecture, right? It's not really a lecture. So you just navigate given the main ideas, and the technical things they can either read in the papers which you have to cite, or they might ask after your presentation, and then again you can either have extra slides with all these technical details, or you can just go to the slide with exactly as you created, but you were going only in a few main points. Now you can go into each line one by one. Because, and of course, connection between how slide number 2 is connected to slide number 10 or whatever slide number 20. And again, it looks like this connection is, for you, of course, it's clear, right? Because you know what you show in slide number 25. We don't know this, right? Because it's the first time for many of people on Monday which we'll see. So for us, this connection completely not obvious, and completely kind of we really don't understand why you were, as Levi said, spending 5 minutes explaining this simple model particle in a box, and then another 15 minutes on all these complicated equations, and then why you need this particle in a box model.
And if you really want to connect it to this slide, you could copy and paste the DOS with
your
boxes
picture from your slide
and
number 2.
put it next to it, because you have a good amount of room on this slide.
Yeah, that makes sense.
But again, returning back to the last piece of equation which we were stopping on methodology. And again, just very briefly, summarize all the things which you were discussing for this methodology. So suppose you're done with all these details, and so what for? What was the main purpose of all these things? why you need this R or K, or whatever your index is.
Oh, sorry, I just need to breathe a little bit. It's the non-radiative recombination rate.
So your main outcome is a non-radiative recombination rates
And cooling.
and
Cooling from the dynamics.
how quickly your excited electron or hole will end up to the edge of the band gap, right?
Mm-hmm.
And your methodology allows to get the rates. The rates are this R is a rate, right? And K is, or K is your rate, what is what?
Well, we approximate non-radiative rate as a Redfield tensor element.
So K is your rate, which you obtained from wherever these equations and equations and that equation. And then the next figure showing, it's not rates. My understanding is couplings or something, or kind of proportional to the electron-photon couplings.
It's this just plotted.
What's the physical meaning of this?
Transition rates between orbitals.
Transition, what? Repeat again, I didn't hear your word.
So they're state-to-state transition rates
Ah, transition rates.
from the non-adiabatic couplings.
State-to-state transition rates, which of course proportional to the non-adiabatic couplings. And then,
Depends on, it's not proportional, it's like square or.
well, yeah, well, some dependence, okay. And then something we really learned from this? Does it have really some main, again, if I don't want to, because there are many, many different peaks here, right? But maybe it's really something important about the most biggest guys. Do they say something to us? Where exactly I should to look on? Like, what is your main point here?
I just put this in here because I didn't show them, I
As
didn't plan on
information.
showing them, yeah.
Okay, then you have to say that all these formulas will end up as a final result the rates between electronic states, which are kind of governed by the non-adiabatic couplings, which we can graphically represent as this, how we call it, matrix? It's not matrix, matrices. As these matrix elements with the height of this each transition rate, I mean, with the height of this each kind of peaks corresponding to this transition rate of this electronic, between this and this electronic levels, right?
Can you go forward to this matrix? So those are occupied orbitals. Those are indices of occupied orbitals as well. So this quadrant corresponds to cooling inside the valence band. This quadrant, so this indices go for unoccupied, and this also somewhere here, yeah, goes for unoccupied. So this quadrant corresponds to cooling of the unoccupied orbitals, from orbital to orbital. This would correspond, like anything in this quadrant, will correspond to transition from between valence and conduction band. And since non-radiative recombination is much slower than non-radiative cooling, the heights of these little one-store houses is much lower than these skyscrapers. And most important, recombination stays here, from HOMO to LUMO. This number, the heights of this little one-store building, is what contributes to the main result. Although this cooling information is also cool. So this number, the heights of this peak in this matrix, is most important product of the simulation. Although other ones are important byproducts. Would it be right? Okay, so we have 6 slides more in the last page.
And now it's really results, right? Now you will give us all physics and chemistry about this system.
Wow.
With the main point to explain what exactly is the question you want to address with all this methodology. I understand it dealing with Polaron, but what exactly is the question you want to address?
Optical transitions and Polarons. The efficiency.
In the presence of Polarons.
Right. Or of the Polaron.
Or maybe you can say how the Polaron affects the optical transition. Is it something? What exactly is the question?
It is the Polaron.
It is
Polaron is absorbing and emitting.
Optical properties of Polaronic states, which are very different from optical properties of
exotonic states.
Yeah.
But is it known? My problem here is I understand the words which you're saying. I don't understand why I need to know about the optical properties of Polaron. Is it measurable thing? It is. Can you just then measure and show the spectra from experiment? Then why you need to do the simulation? Like, are you just want to replicate the experimental observables, the experimental spectra of these Polaronic states? This is the main goal, just to be able, like, is your main goal just to justify that your methodology works, so you have experimental things, you do your computations, and just compare one-to-one your Polaronic spectra and say, oh, it agrees, great, so our methodology is correct, or is trustable. This is one goal. Another goal, you say, well, I think my methodology is trustable because it was applied to many other systems, and now I want to learn new things, or maybe interpret experimental data, or predict something new based on these results of the methodology. What is your point for describing the optical Polarons?
Predict something new.
And wait, it's not all. It's not all, and he did, but it's not all. There are experimental results on Polaronic optical properties.
Yes.
But there is no experimental control of whether negative Polarons, positive Polarons, or they both together
Negative
contribute.
electron hole. Oh, you mean
There are negative Polarons and positive Polarons.
just based on the electric constant direction?
No. Regions of material can be charged negatively and positively. Negative and positive Polarons can be created not only by optical excitation, by charge injection. And optical properties of negative and
But
positive, please wait. Negative and positive Polarons have very different optical properties, very different optical signatures. In the experimental signal, both of them contribute, and there is no opportunity to dissect which of the signals, which of the peaks contribute from negative from the positive. Computational simulation allows to dissect and consider them separately, and
So
like
you want-
expand experimental results even if they are available
technically-
over the basis of elementary processes. Therefore, computational modeling is critically needed to analysis of this problem.
This is all great, but I didn't hear it from him, and I thought it's his talk, not yours. Am I right?
He meant to say this. Okay, so let's finish the results, which are like the last 6 slides.
So I was done showing the symmetry of the orbitals. So now, moving on to modeling the dynamics of the charge neutral model. And so the screen, or this figure here, shows the dynamics of excited state energies after the photoexcitation. So this is the photoexcitation creating a hole in an electron. And then as time moves on, they interact with the lattice and they cool to the band edges with a certain amount of time. And then eventually at some time they'll decay. And so the interesting thing with this figure is if you look at the figure of the electron, normally you'd expect like the occupations do decay pretty quickly or uniformly, but you see like an extended stretch of occupied state as it cools down to the state. So that kind of suggests that there's a longer excited lifetime for the photoexcited electron compared to the hole. And so that's what this figure plot here is here. So it's the same curve, just normalized to a dimensionless energy. And we see that along the trajectory, or I guess I'll back up. So this is plots two figures. So the red dotted is a single exponential fit. So if you just assumed it was a single decay. And then the black line is what we actually compute during the dynamics. And you can see as it cools down to the band edges, here that it's kind of, it initially decays quicker, but then as it cools down near to the edge, that it has an extended tail on it. And so that kind of indicates that there's a slight phonon bottleneck here, and we attribute this to the large subgap between the two lowest energy states. So it's about a 0.2 eV energy difference. And so we published that in a paper recently. And based on this,
and this splitting between these two levels connected to the idea that this is a strongly bound polaronic state, right?
or this is charge neutral. So this is just from, yeah, I should have mentioned that.
Or it's just without Polarons?
This is without Polaron.
Oh,
So this is charge
so just
neutral.
intrinsic property of this electronic structure.
Yeah, this is due to Spinor coupling. So, yeah, I guess I didn't give any background before, but it reduces the band edge energy by about 0.7 eV compared to if you don't include spin orbit coupling into the calculations. So what it does is it creates like a sparse density of states. So you have a low density of states with large energy splittings. So you get slow transition rates between them. And so that's kind of interesting in itself. But if you wanted, or you think about it in a different way. So if you have slow rates of cooling, it could be possible to get rates of emission from those states as well that could possibly compete with it. So if you did put a photoexcited carrier in there, if you slow down the non-radiative rate, it might make the radiative more competitive so you can get emission out of it. And this 0.2 EV band gap is about in an IR spectrum, so it would be a potential IR source. So that's kind of the point of this slide. And so that's when we move on to modeling Polarons for the system. And so this figure is just kind of illustrating. So this is all the colored lines represent the geometry of the Perovskite quantum dot. And then these black solid lines represent you've an added additional charge to the model. And then these arrows represent the response of the nuclei due to that charge. So it's just illustrating Polaron model. And so the first couple of slides are going to be on the ground state structure for the Polaron models in general, and then the IR spectra. And so here is the density states for the, if you consider valence and conduction band, but since for this we're considering the positive Polarons, so we're going to look at the whole states, which are down here. And so we zoom in here and we have 3 different plots for 3 different electronic state or configurations. So you can have singlet, doublet, or triplet. You can get a singlet or triplet by removing 2 charges, doublet by removing 1. And so that's the difference in the area between these.
I'm sorry, which one were your whole states?
All 3 of them are. So they're all, so this.
Okay, I see now that your dot where it's going.
So yeah, colored region represents occupied. The white represents unoccupied. So that'd be the whole. And so, and that's why this one's colored in a little bit more. Only 1 electron. And you can see they have approximately, show some sort of symmetry peaks for all those. And so those are the density states. You can consider optical transitions between them. So this is a computed IR absorption plot. So it's plotted in wave number because that's usually what experimentalists use for IR spectra. You can see for the triplet and the singlet, it's got bright peaks around 500 wave number, and that's, I think it's like 0.1 eV, maybe close in that energy range. Then the doublet is a little higher in energy and it's less intense. So the doublet looks less promising for an IR source. And then this is the same figure except for the negative polarons. So we focus on the conduction band states. And the colored in regions represent or show that we added a charge to those states. And so single and triplet, again, we added 2, doublet, we added 1, so it's half occupied. Because each state is twice degenerate, so that's why it's only half filled in. And again, we can look at optical transitions between all these peaks. For the Polaron, you can see for the single and the triplet, they both have intense IR absorption too, even brighter than the positive Polaron. And then the doublet is there as well, and they're all about the same energy of 1500 wave numbers, and that's about 0.2 ED. And so, in terms of emitters, the triplet and the single look more promising to get IR emission out of compared to the doublet for when we go to our dynamics. And so, we only have results for our positive Polarons for now, so it's the whole states, yeah.
Why is it that you're seeing that the doublet's not going to be beneficial for you? What's the fundamental understanding of that?
Well, I guess it shows less. So absorption and emission are inverse processes. So if it's a good absorber, it's good. It could potentially be a good emission.
That's just the. I'm just curious. I'm just curious if there's any other besides fundamentally what we see on the graph, or is there kind of something more background? I just didn't know.
I guess those are also the lowest energy transitions. So if you're going to see PL, that's where they would come from. So that's why I pointed those ones out.
So how do you get singlet, doublet, and triplet out of this one system that's negatively charged?
So it's plain.
Because typically you either have odd or even multiplicity. You don't have both. Like you either have singlet, triplet, pentet, and so forth, or doublet, quartet, sextet.
Are you talking about how we get the occupation?
No, like
Because again, which atoms you have there? Some of these atoms don't have even number of electrons, right?
Right, each band is twice degenerate. Is that what you're asking?
I guess what I'm
No, he's
asking
saying that if you have neutral system, you add the electron. It's a single electron, right? With only this specific spin.
Right, that's a doublet.
And then you can create only, when you excite it, you can create only doublet, right?
Right.
But you cannot create singlet or triplet from a single electron.
So just explain procedure.
So how you get into
are you
triplet
adding
singlet?
or removing one electron or not only one?
I know I mentioned it, but I think, so for single and triplet, it's 2 charges. So then you can have them aligned or parallel. And the doublet's only
And
one.
why you have 2 charges? Because you add only one single electron. How it appears two electrons?
No, once again, do you add or remove always one electron or more than one electron? Just to pronounce it.
More than one, or
So these are different simulations.
Charges. So then number of electrons is different in between these pictures, right?
so singlet and triplet have the same number of electrons.
Right.
Doublet has one less.
You might want to show that. I don't know.
I don't know, I thought,
I probably just missed it when you were talking.
You did say that.
Something else.
In the beginning, right? When he's
No, he said it like maybe when he was explaining the last slide, he said that.
Maybe highlight it. Like white slide is only one line. I remove more than one electron. Period.
No, I just probably should have done this more closely.
In other words, you're just creating different polarons there, right? Like for your doublet, triplet, and singlet, it's different polarons.
Exactly. It is
Right.
the same question like on experiment. Who knows?
Which one is which one?
Yes.
But
yes.
you can make them really one by one.
Dissect nature on the elementary processes.
and so this is just some of the dynamics for the positive Polaron. So we've data for the singlet and the doublet so far. And so the way to read these figures is I tried to help putting in these sidebands. So to create these states, you'd have to inject a charge. So we imagine that you have some sort of lead connecting to the valence band. So you inject a charge into what would be a valence band state, and then eventually cool to what's normally called the relaxed excited state. And then from this state, it would either radiatively or non-radiatively recombine to the lowest state. So this figure just shows the amount of time it takes to cool to that relaxed excited state. And it's pretty comparable to, the neutral model. It's pretty much the same rates. It's on the sub-picosecond scale on 100 femtoseconds. So that's the cooling.
Wait, sorry, to go back to that slide. How, could you explain like 2 words how the left is describing the right?
Oh, how to interpret color code?
Well, no, the equations, how the equations are interpreting, or how the graph is interpreting the left-hand equations, just briefly, how I see that, what I see on the graph is really good.
So the energies are represented by solid or dashed lines. So that's expectation value. That's just based on occupations. And then the colors come from this term. So green is background, so neutral. Blue is whole.
Rho in your formula, this is your coefficient number, or what is it?
Or yeah, it's a density, occupation density, right? The occupation of an electronic state.
Time-dependent occupation number for this.
Yeah, so that's how to read the color codes there. So blue
Like
is
your-
whole cooling. And
Your
then-
rho is really kind of responsible for these different colors.
right, because
Going
that's
from whatever, dark blue to light yellow.
yes, because the populations change in time. So that means this guy's changing in time. And then, so that was non-radiative dynamics I showed before, but you can also compute radiative dynamics along this trajectory. So you can try to plot the probability that it's going to emit a photon as it cools to the band edges. And so the blue means there's no signal or no bright intensity or bright transitions available. Yellow indicates brightest, and then other colors represent in between. And so basically, you see early in the dynamics for both those figures, there's at least three sets of occupations that show kind of faint transitions. So that'd be kind of analogous to this picture here, where it's, if it was in this occupation, you could have all sorts of possible transitions from that one occupied state. And then eventually, as it cools to the band edge, you get some emission for the singlet as well. And then once it gets to the relaxed, excited state, it has a bright optical transition from there. Whereas for the doublet, once it cools to the band edge, its lowest transition energy is 0. So it's basically just nothing there.
And these equations, the time resolved and the time integrated, relate to these?
And so time resolved is the blue figure, because those are in time. So at each time step, it calculates the probability of a photon emission. And then this white figure just sums everything together. And so for the singlet, like there's only one big peak, because the most prominent comes from like this yellow bar, and it's there for a lot longer time. Whereas with the double, you see 3 low intensity peaks, which don't have a lot of signal. And I think this is the last slide. So from the data, I didn't show how we calculated radiative recombination rates, but you can use Einstein coefficients, which basically just involve oscillator strengths and transition energies. And so for both the singlet and the doublet, their radiative recombination rates are on the scale of inverse micro, 10 to the 6. Is that micro? So microseconds. Whereas the non-radiative cooling rates, or non-radiative recombination rates from the Redfield tensors on the scale of inverse picoseconds, so there's 6 orders of magnitude difference, or the non-radiative is 6 order of magnitudes quicker, so you essentially have a 0% quantum yield.
And if it diverges from experiment, it will mean that something is wrong with calculation.
But you said they has to be bright, but quantum would
Wait. On one hand, there are results for emission, Polaronic emission. On another hand, there is a comparison of radiative and non-radiative channels of relaxation. And it looks like radiative is 6 orders of magnitude weaker than non-radiative, which is either means that on any experiment there will be no Polaronic emission from this material, or it means that something is missing in this theory.
And do we know this experimental data? What they quantum is what they assign as Polaronic emission?
Available experimental data are in the infancy. They just make in the infancy, like they are like very early and not many details. So it is an attempt to compute forward before experiment is ready.
So nothing is available to compare directly.
I've seen
indirectly at least.
I've seen results for absorption for thin films of the same material.
Okay.
But I haven't seen any results for emission yet, or efficient emission anyway.
But in your case, emission and absorption will be the same.
Right.
No. This is emission. Is it labeled on the slide?
Well, I mean.
Wait. Let's.
Just completely reverse processes.
No. They are very different. So let's go 2-3 slides back. So here is the absorption. So absorption has many peaks, right? So you are looking on the upper right. And emission has only lowest of these peaks.
Of course, because you look on the emission from the lowest. But if I go with the energy range, I don't know, wherever, because here is the energy from volts and here is centimeters in the big numbers. So, but if I take from 6,000 to 500, this probably will be the range which is showing for your emission.
The lowest peak should be
The emission.
And this is the last slide.
Yes. So I haven't filled it in yet, but basically, positive Polaron, probably not going to be the source of any IR emission if they do find them in these materials. And works on going for negative Polarons and eventually a charge neutral. So, or simultaneous positive and negative Polaron.
Are there expectations that negative Polaron or simultaneous coexistence of negative and positive will be more emissive than positive?
Based on this trend here, I would expect. Well, going in, I would have expected the negative, if there was going to be a bright emitter, it would have been from the negative, just due to the slow cooling in the conduction band that we find anyway.
So are your Polarons located at some specific part of your crystal, like a specific, like are they coupled really to specific motion of atoms? Because it has to be very localized state, right?
Right.
Localized on somewhere.
I guess it's,
Are they really localized somewhere? Can you?
I guess I didn't put any orbitals on there, but they,
And do you have different localization of positive and negative Polarons? Let's say your negative might be more localized on cesium, and your positive will be more localized on, I don't know, on lead, for example.
the
Yeah, you
conduction
can
band.
take probably the difference between density of states for charge density of states.
Positive on bromine, negative on lead.
Okay, so you know it for sure, or you just
Oh,
like,
yeah.
or you just assume it based on the charges of your atoms. But emphasizing on the bromine and lead. I don't know, you have your figure results Polaron, right? Like the slide number.
Yes, and this figure is
Number 20.
extremely needed because you cannot speak about Polaron based on charges. It's only how much each of ion is displaced.
Right, but does this figure really, just help me to read it, does it really kind of give this information which Dmitry said, that your negative Polaron is expected to be more localized on bromines? Bromines?
Lead atoms, lead P atoms.
Negative? Negative
The
on
negative.
lead?
Mm-hmm.
Negative on lead.
And why? How you read this figure? Why? Convince me. So these black lines mean what?
Isosurface of the added charge.
Which charge, plus or minus?
Minus.
In this case, black lines corresponds to the most localized negative charge on whatever atoms are in this, around these black circles, right?
Mm-hmm.
And this is what you're saying it's lead?
Yes. And the arrows show
And
response.
then where's your negative charge then? I mean, negative Polaron, is it only for positive Polaron or it's both?
This is just negative.
Oh,
So this is
negative Polaron.
adding one negative charge.
And if you add in positive charge, picture is different.
It would
Probably show two pictures to compare.
be delocalized, or
More delocalized. So your whole is also more delocalized, I mean, your, not whole, how you say it, your positive Polaron is more localized, more delocalized comparing to negative Polaron.
yes, because where's that orbital picture? This is basically what the whole Polaron would look like. This is for charge neutral, but the orbital pretty much stays the same if you remove or if you leave it unoccupied. So it would have S symmetry throughout the whole box. And I guess it's awkward for our model to talk about whether it's localized or not, because it's such a small model. Everything's going to be localized. So you don't really see much charge separation between the positive and negative Polaron. Whereas if it was in a thin film, they would break away.
Mm-hmm. So if comparing from ideal, perfect discussion of these results, it looks like from 4 components, 2 are present and 2 are missing. So for negative Polaron, one needs the distribution of charge and displacement of ions, and it's shown only distribution of charge. And for negative, it's also needed distribution of charge and displacements of ions, and it is shown only displacements of ions.
So this is not moving. This is not the movie by itself, or it does. Like it's showing this, arrows showing the motion of these atoms, right?
Right, so all of the atoms, that's the neutral geometry.
So
then it's adding 1 charge into the box. That's these orbitals. And then these arrows show the response of the cesium nuclei to this charge. With the dramatized arrows, just to emphasize that they're moving.
I remember you were showing some kind of movie, or maybe it was not you. It was a movie, you cannot make a movie to really see this redistribution connected to the motion of atoms.
it is possible, but not in like 2-3 days.
And it's very slight, like it's not a dramatic
Not visible.
change. Yeah, you wouldn't notice it by the naked eye.
Typical nuclear reorganization is like 1% of interatomic distances, so it will be not much visible by human eyes.
But it does reduce
But the orbital will be changed
a little bit.
more.
A little bit, yes.
And again,
Less
you can
symmetry.
always take the difference between charged versus not charged.
Like
And then maybe
take orbital from non-charged, take orbital of the same symmetry upon formation of Polaron, and subtract these 2 charge densities and show regions of space where they're different. Of course, it's not for Monday presentation, but general idea.
because again, if you expect such a big difference in behavior for optical response of plus versus negative, positive versus negative Polarons, right? Again, the question would be why, and then this kind of information where they're localized, how their orbitals are affected by whatever localization to localization properties probably would be a good way to use to explain why, even if you don't have data, but you expect at least that negative would be more optically active because it's more localized. That's why. Actually, then again,
There are several
factors.
So one, and we do not know yet which of them is more efficient. One is that they are more localized. Another that is already pronounced in the neutral system, that the offset of conduction band H, Luma and Luma +1, is increased due to spin orbit. So it's both localization and spin orbit may favorably affect the ability of negative Polaron to emit light.
And it is the right size of Polaron too, like compared to, I mentioned in the introduction, but it has the right coupling parameter. It's like the right size of Polaron, or like the right type of coupling. So it has stable optical transition, or stable like electronic states, or it should anyway, if the theory is right.
Okay, let's thank Aaron. Are there any post-upload questions? If not, let's submit written feedback to the author.
So while we're doing it, on slide 4, do you know why they don't do a mixture between chlorine and iodide? Because I would assume that that would cause the same effect as mixing iodide with bromine, where you get like a pseudo, like you could make then from this color all the way to here, depending on the amount of each ion, and then you wouldn't have to deal with having 3 different types of that ion. You just do 2 and look at the mixture of the 2.
I hear what you're saying. I think it's just fine.
Oh, okay.
You try to put them, it's just not a stable pattern.
Oh, that makes sense.
Okay, well, thanks to everyone for intellectually contributing. Let's wish Aaron safe drive and safe return.
How long it takes you to drive? 6 hours?
5.
5?
Oh, that's decent.
Well,
Where are you
Well, if
driving
you
to?
don't stop, I guess, right? 5 is no stops in the run.
yeah.
You probably have to stop. You cannot drive for 5 hours without.
Yeah.
I like stopping in Hudson.
Huh?
I like stopping in Hudson.
And
But if you only have to drive
I
5
guess
hours,
if
that's obviously
you
the drive.
have a